Swayam Prabha. Digital India. Educated India.
In lecture 32, we looked at Stefan flow model, which is essentially a diffusion model to be applied to stagnant surroundings, and therefore momentum equation was not invoked, only the species transfer and the energy equations were invoked. And we applied these equations to the three types of mass transfer that or four types of mass transfer that we normally encounter. The one is the inert mass transfer without heat transfer, inert mass transfer with heat transfer, then mass transfer with heat transfer and simple chemical reaction, and then finally we applied it to the case of mass transfer with arbitrary chemical reaction. All these four types are most describe the overall problem of mass transfer. Today we are going to consider the Couette flow model, and therefore we shall be invoking both the momentum equation and continuity equation along with the species transfer and the energy equation. So, we shall apply the Couette flow model to mass transfer with wall suction and blowing. This is essentially a case of, let us say, air flowing over surface and air itself is being sucked or blown through the wall, which would be the simple case of suction and blowing that we considered even with similarity solutions. Then we will move to the general problem of convective mass transfer, and in this we shall interpret the effective mass transfer coefficient, which we shall term as G star, and by way of an example we will calculate estimate the evaporation / burning time of a liquid droplet. So, let us begin then with the momentum transfer with wall suction and blowing. Now, in the Couette flow model, as you will recall, the velocity u is taken to be constant multiplied by y, and all actual derivatives are set to 0, and therefore a is constant, and hence under steady state transport equation would read like this: d by dy of n psi y equal to d by dy of rho mv psi minus gamma plus gamma t, where gamma t is the turbulent exchange coefficient, d psi by dy equal to s psi. Just by way of reminder, the Couette flow model is really, let us say this is the surface, and we assume that the velocity profile will be like so, with u infinity here. All d by dx are 0 for all variables, and u infinity remains constant along the plate, and this is the direction y. So, this is really the Couette flow model. The mass transfer would be taking place in this direction. So, if you look at the meanings of psi, psi equal to 1 would imply simply continuity equation or mass conservation equation. Psi equal to u will imply momentum equation, which gamma equal to mu, and then if it is a mass transfer, mass fraction omega k, this would be the species transfer equation, and this would be the energy equation. We have ignored the radiation and other heat generation terms here. M double dot y k is really the Fick's law of diffusion flux given by the Fick's law, and rho mva will be m dot w is equal to constant, which is the mass flux would remain constant. So, let us consider momentum transfer. So, if psi is equal to u, then the governing equation Remember that there is no source term here, but the pressure gradient is also 0, and therefore, the equation will be d by dy NWU minus mu plus mu t du by dy equal to 0. If I integrate this once and note that the boundary condition is u equal to 0 at y is equal to 0, so shear stress is given by mu times du by dy y equal to 0. Of course, mu t would be 0 at the wall. The constant of integration c will be simply minus tau wall, and hence the integrating from 0 to infinity would give me du divided by NWU tau w equal to 0 to delta dy mu plus mu t, which I am for the moment calling it as constant C1, some integral value, integrated value C1. And the integration of this term would simply result in 1 over NW ln 1 plus NWU infinity by tau w. But what is NWU infinity by tau w? We can interpret that. Remember, NW is rho times VW, because the same air, same fluid is being blown into the boundary layer as is flowing over a plate. Rho VW u infinity divided by tau wall. If I multiply and divide this by u infinity, then I would get VW divided by u infinity equal to rho u infinity square by tau w, which is nothing but VW by u infinity CFX by 2. And as you will recall, this is nothing but the blowing parameter, which we had invoked during similarity solutions and integral solutions. So, essentially then NW would be 1 over NW ln 1 plus BF would equal some constant C1. So, that is what I have written here. Ln 1 plus BF would equal C1 times NW, and C1 rho u infinity BF over CFX by 2, because NW is rho VW, which can be written as rho u infinity BF CFX by 2. Now, of course, as BF tends to 0, the CFX must tend to CFX at VW equal to 0, and then assuming that this integration, that is integration 0 to delta mu plus mu t, would remain the same whether there is mass transfer at the wall or no mass transfer at the wall, which of course would be exactly true if it was a laminar boundary layer. But even in turbulent boundary layer, if we say that mu t essentially is a function of y and not affected by whether, as you will recall from Prandtl's mixing length, that it will not be too seriously affected. If we assume C1 is independent of whether VW is finite or 0, we can show that it follows from this equation that CFX VW divided by CFX VW 0 would be ln 1 plus BF by BF. This equation is applicable to both laminar and turbulent flows, and it is derived for dP dx equal to 0, but can be taken to be valid even for mild pressure gradients, as was done during integral analysis of momentum equations in our previous analysis of fluid flow problems. Now, for all 4 types of mass transfer, I am not going to rederive as I did in case of stiffened flow. I will simply say that in each case we simply converted the applicable mass transfer and energy transfer equation to a conserved property equation with appropriately defined conserved property psi. So, for all types of mass transfer and an appropriately defined conserved property psi, NW will be equal to n psi y equal to constant, and hence for conserved property instead of psi I can also take psi minus psi w as a conserved property. Then NW into psi minus psi w gamma plus gamma t d by dy psi minus psi w is equal to 0, or NW into psi minus psi w minus omega minus gamma plus gamma t d psi by dy equal to C1, some constant C1 now. Remember, d psi omega d psi w by dy is of course always 0, so that does not appear here, but d psi by dy would certainly survive. Then if I write this equation in the w state, then I would get C1 equal to gamma d psi by dy at y equal to 0, And if I write it in the t state, I will get NW psi minus psi t minus psi w, and in the t state there are no variations of psi, and therefore, this entire term would be 0 and again C 1, and therefore, equating the two equations because they are both equal to C 1, I would get C 1 equal to NW psi t minus psi w equal to minus gamma d psi by dy at w. This is and at the w state, of course, omega t gamma t is equal to 0. So, that is what I have stated here. We shall make use of this equation and substitute for C 1 here, C 1 equal to N w psi t minus psi w. I will substitute that here on the next slide, and you will see that therefore, I would get N w psi minus psi t minus gamma plus gamma t d psi by dy equal to 0. If I integrate this equation from w state y equal to 0 to infinity state y equal to delta, then I will get 1 over N w equal to 0 to infinity d psi by dy, d psi by psi minus psi t equal to 0 to delta dy gamma plus gamma t, where gamma in case of energy, gamma is k by Cp. In case of species transfer, it is rho m times diffusivity. So, let us say that integral, like in the previous case, we will say is equal to C 2, let us say. Then the integration of the left hand side would give me N w equal to 1 over C 2 ln 1 plus b psi, because same as previous case, b psi is equal to C psi infinity minus psi w divided by psi w minus psi t, and N w will be from the previous slide, N w would be C 1 divided by psi t minus psi w, and that would equal minus gamma d psi by dy at w psi t minus psi w. So, we have got one equation which is of this form and the other equation which is of this form, the first containing C 2 and the second containing C 1. So, now consistent with the theory of heat transfer, we may write minus gamma d psi by dy at w is equal to g times psi w minus psi infinity, where g is now the mass transfer coefficient. So, if I replace this quantity by this quantity in the previous expression here, then I get C 1 would be I can get C 1 from there in terms of g, and therefore, the final form would look like N w equal to g times psi infinity minus psi w divided by psi w minus psi t, or simply g times b psi, and g itself would be 1 over C 2 times ln 1 plus b psi divided by b psi. Now, if I assume that as b psi tends to 0, g tends to g star, the mass transfer coefficient, let us say it tends to g star corresponding to b psi tending to 0. Further, and if I say that C 2 remains constant with or without mass transfer, as we said earlier, this statement is of course perfectly true for laminar boundary layer, but even if I say it is true for turbulent boundary layer, where 1 over where gamma t would be a function of y, then it follows that g over g star would be simply ln 1 plus b psi by b psi. This is a very important result. Thus, the fictitious g star flux is now given by N w g star ln 1 plus b psi, where 1 over g star is equal to C 2, which is equal to 0 to delta dy over gamma plus gamma t. So, we can now view g star itself as the sum of layer by layer from 0 to delta resistances to mass transfer in the considered phase over the width delta, because remember this is the diffusion coefficient. So, 1 over diffusion coefficient would simply be resistance, and we are simply saying that 1 over g star which itself is a kind of a resistance, because g star is conductance, then 1 over g star would be simply layer by layer addition of resistances to mass transfer in the considered phase. This interpretation of G star enables its evaluation from gamma y equal to gamma psi in a laminar boundary layer, and from the known gamma T y from a turbulence model like a mixing length, or for example in a turbulent boundary layer. Thus, the Couette flow model permits study of the property variations. Remember, gamma itself could be a function of psi, of temperature or the mass fraction itself. Gamma T on the other hand would be a function of the turbulence characteristics of the boundary layer. In fact, if gamma is equal to constant and gamma T is equal to 0, which is the case of a laminar diffusion problem, then G star would be simply gamma by delta, which is same as the Stefan flow model, in which G star was shown to be equal to gamma by L. We have recovered most of the features of the Stefan flow model for gamma equal to constant and gamma T equal to 0, and G star would then be gamma by L ln 1 plus B psi, which is what we had shown in the Stefan flow model. Now, if we consider the case of pure heat transfer in the presence of suction and blowing, something we have solved by similarity method, then with psi is equal to Hm equal to Cpt, because it is an inert situation, just a considered phase as air flowing over it, and suction and blown fluid is the same as the fluid in the considered phase. Its temperature may be same or different, that does not matter, but therefore, we would get minus k dt dy equal to 0, which is the heat flux, and that would equal G times Cp into Tw minus T infinity according to our model, and that would equal heat transfer coefficient for suction and blowing into Tw minus T infinity. So, that is what the heat transfer coefficient is, and therefore, we deduce that the heat transfer coefficient for finite Vw is nothing but G by Cp, and likewise H of Vw equal to 0, that is in the absence of mass transfer, would be equal to G star by Cp, because G star is a value of G when Vw is equal to 0, and therefore, we deduce that G over G star would also be equal to H of Vw divided by H of Vw 0 equal to Stanton x at Vw for Vw divided by Stanton x for Vw equal to 0, and that would equal ln Bh by Bh, where Bh now is T infinity minus Tw over Tw minus Tt, because specific heats in all states are taken to be constant at the moment. So, now this relation was found to be applicable in real boundary layer flow in lecture 30, you will recall, and therefore, the Couette flow model captures also the features of a real boundary layer flow. So, the Couette flow model on the one hand, when gamma T is 0, captures the Stefan flow model features, and it also captures the boundary layer flow features. At least when the species are the same, it captures both the features very well. Now, we turn to the application of this to evaporation and burning, in which we shall invoke the previous expression for can be used instantaneously to estimate the evaporation or burning times. Thus, let us say if I have rho L dV by dt is equal to minus m dot w, which is the rate of change of mass, is equal to minus m dot w kg per second, and that would equal A w n w, and that would equal minus A w G star ln 1 plus B psi, where A w is the area of the surface through which the mass transfer is taking place. Then integrating this from time t equal to 0 to complete evaporation when the volume disappears gives us the relationship T evaporation or burn is equal to minus rho L ln 1 plus B psi equal to V initial to 0 dV by AWG star. Now, let us say if we are considering a liquid droplet and diffusion mass transfer, that is gamma T is equal to 0, then AW will be equal to 4 pi RW square, V will be 4 pi 3 pi RW square, and G star will be gamma h by RW, as you will recall. Then hence you will see that evaporation or burning time would be minus rho L divided by 1 over B psi, RWI to 0, RW by gamma mh drw, and that will yield the so called d squared law, rho L dwi squared 8 times gamma h ln 1 plus B psi. And this expression is used extensively in designing dryers and so on and so forth, because all it says is that if you reduce, the smaller the diameter of the droplet, faster will be the drying achieved, because if you reduce the diameter by a factor of 2, the evaporation time will reduce by a factor of 4. In stagnant surroundings, this would be considered as a guidance for atomization of fuels, atomization of, let us say, milk, which is to be dried into a powder, and or in a cooling tower where you send hot cooling water for cooling purposes. Then in a shower, then you want to reduce the diameter as small as possible, so that you get very quick drying and a smaller dryer or a cooling tower. Now, let us say the liquid droplet was in a convective environment, as in inside a diesel engine, where, as you know, in a diesel engine the liquid droplets are injected in an atomized state, and they come out like a cloud, and when the piston is at the top dead center, the temperature is already very high in the surroundings, and the droplets evaporate and then burn inside the cylinder. So, we can assess such, we can evaluate the evaporation or drying times for evaporation or burning times in such situations. But the environment there is convective, because the piston's head is modeled in such a way that there is a swirl inside the cylinder. So, the air movement and the particle and the droplet movement, there is a relative velocity between them. So, essentially you get now convective evaporation or convective drying. Same thing happens when you have a cooling tower, where the droplet is falling down through, let us say, stagnant air, but that sets up a resultant velocity between the droplet and the surrounding air, which is stagnant. On the other hand, in thermal power stations, we have you will recall that we have cooling towers like that, and air ingress like this, and on here you have showers of water, where the cooling water from the condenser falls down, and there is an air. So, you have a counter current of air and water, and therefore, the liquid droplets evaporate under counter flow. So, the relative velocity is additive of the air flow and the water flow, droplet flow, which is coming downstairs. In the process, the water gets cooled and is sent back to condenser. Of course, some amount of water is lost, because the air moving upwards picks up some moisture, which has to be topped up, of course, from time to time, so that the condenser is not starved of cooled water. So, in such situation, we can use a shortcut method, and thus we can say that m dot w, that is mass transfer rate under convection divided by mass transfer rate under diffusion, would be mass transfer rate under convection according to the Couette flow model is G star times AW, which is 4 pi RW squared ln 1 plus B, and mass transfer rate according to diffusion model, which is the Stefan flow model, is rho md 4 times pi RW into ln 1 plus B, and therefore, cancelling the terms, you will get 1 over 2 G star dW, which is the diameter of the droplet, divided by rho m diffusivity. And this quantity, like Nusselt number, is called the Sherwood number. Yes, in mass transfer, the analogous to Nusselt number, we have a Sherwood number, which is essentially G star, the mass transfer coefficient into the diameter divided by rho m d, which is equivalent of the conductivity of the fluid. Now, if I use analogy between heat and mass transfer for Lewis number 1, then you know that for a flow over a sphere, you know that the Nusselt number is 2 plus 0.6 Reynolds raised to 0.5 Prandtl raised to 1/3, but I can now say Sherwood number would be 2 times 0.6 Re raised to 0.5 Schmidt number raised to 1/3, where Re is based on the relative velocity between the gas and the droplet, the diameter of the droplet, and the kinematic viscosity. Or this expression, for example, will now get changed to 2 times rho L ln 1 plus b psi Rwi to 0 Rw drw divided by gamma h 2 plus 0.6 Re dw 0.5 Schmidt number raised to 1/3. Now, since this also contains the radius Rw, because dw is 2 times Rw, this expression integration requires numerical integration because closed form solutions are not found. So, let us take for example, if I took a problem, let us say a water droplet dwi is 1 millimeter diameter at 25 degrees centigrade evaporates in air whose relative humidity is let us say 25%, then and temperature is 25 degrees centigrade. So, that this is a case of mass transfer without heat transfer and no chemical reaction. And let us assume that the relative velocity between the two is 5 meters per second. So, estimate the evaporation time and take Schmidt number equal to 0.6, which is quite typical of gaseous mixtures. So, this is a inert mass transfer problem without heat transfer. The mass fractions are in the infinity state corresponding to 25% RH and T equal to 25 will give you omega V infinity equal to 0.0078. Omega V W corresponding to 100% relative humidity at the droplet surface and 25 degrees centigrade will be 0.02. Bm would be omega vapor in the infinity state minus omega vapor in the W state, and omega vapor in the W state minus in the T state, which is the transfer surface, and that would be equal to 1. So, using this definition for omega V, as we did in the in problems on diffusion mass transfer, the Bm would turn out to be 0.0124. At the mean conditions between the infinity and W states, mixture density can be evaluated as 1.177 kilograms per meter cube. Liquid density would be 1000 kg per meter cube, where it is water. Diffusivity, from the lectures we say that the diffusivity of water vapor through air is 2.376 into 10 raised to minus 5, and nu m will be diffusivity into Schmidt number, which will be equal to 1.42 into 10 raised to minus 6. So, knowing nu m, we can evaluate, and u relative, we can evaluate the Reynolds number that is required here in the Reynolds number expression, and dm, which is required here to calculate gamma h, because this is rho m times dm. So, we can carry out the numerical integration with time step 0.01 second. Then evaporation time at Rw equal to 0 would be 2.05 second, and the radius would vary in this fashion, 0.5 mm to start with, and then it drops down very gradually to 0 value here at about 2.055 seconds. Now, we can solve the same problem in stagnant surroundings by simply setting u relative equal to 0, which means that the Reynolds number here is 0, and therefore, this will be 2 times gamma h. Then you will see that that the evaporation time becomes 4.66 seconds. So, clearly having a relative velocity between the gas and the droplet has reduced the evaporation time, and this is the principle that is used in cooling towers and in diesel engines for the purposes of reducing the size of in case of cooling towers, and in diesel engines this is of great value because it enhances the rate of burning of the fuel, and which incidentally also reduces the cutoff ratio of a diesel engine, which in turn improves the efficiency of the engine. So, finally, in summary then we can say that the Couette flow model with area equal to constant and u equal to constant times y and d psi by dx equal to 0 gives us the formula Nw equal to G star ln 1 plus B psi, where G over G star is equal to ln 1 plus B psi by B psi. We interpreted the G star flux as the sum of the layer by layer resistances to mass transfer in the considered phase over boundary layer width. In pure momentum and heat transfer, in the presence of suction and blowing, that is without gradients of species of any kind, because the same species being sucked or blown, we have shown that Cfx in the presence of suction and blowing divided by Cfx in the absence of it is simply ln 1 plus Bf by Bf, and the heat transfer likewise would be ln 1 plus Bh by Bh. So, Couette flow model recovers essentially the results expected from a boundary layer flow model. It also recovers the results expected from the Stefan flow model, and in turn gives us an opportunity to evaluate the effect of property variations, which we shall take up in subsequent lectures. So, in the next lectures, we will develop very similar results to what we have shown in Couette flow model via the algebraic Reynolds flow model, and you will see what form N, W and B relation has as per the algebraic Reynolds flow model.